The Signal Filter Registry is a singleton component responsible for managing filter instance allocation, lifecycle tracking, and configuration persistence across the application runtime. The registry maintains an internal hash table indexed by filter identifier strings. All operations against the registry are protected by reader-writer locks to ensure consistency under concurrent access patterns. The registry does not perform actual signal processing, it serves purely as a management layer. Filter registration is accomplished through the register method, which accepts a filter identifier, a factory function pointer, and an optional configuration object. The method performs validation of the identifier string to ensure it conforms to the naming convention. Alphanumeric characters and underscores only, maximum length of 64 bytes. Duplicate identifiers are rejected with an error code of filter already registered. The factory function is stored without invocation. The instantiate method creates a new filter instance by invoking the stored factory function associated with a given identifier. If the identifier does not exist, the method returns a null pointer and records an error code of filter not found in the error state. Instantiation does not modify the registry state directly. The instance lifetime is managed by the caller. Multiple instantiations of the same filter type are permitted. Configuration parameters for filters are stored separately in a configuration table that maps filter identifiers to parameter sets. Each parameter set is represented as a key-value structure using string keys and variant-typed values. The set configuration method updates or inserts a parameter set without affecting registered factory functions. The configuration exists method returns a Boolean indicating whether parameters have been stored for a given filter identifier. Filter removal is performed via the onRegister method, which accepts a filter identifier and removes the associated factory function from the registry. Unregistration does not affect existing instances created from that filter type. If instances are still active when unregistration occurs, they continue to operate normally until their own destruction. Subsequent calls to instantiate with that identifier will fail. The list_registered method returns an ordered array of all filter identifiers currently registered in the registry. The array is sorted lexicographically and does not include metadata about factory functions or configuration status. The returned array is a copy of the internal list. Modifications to the returned array do not affect the registry state. The array is allocated dynamically and must be freed by the caller. Thread safety is maintained through a reader-writer lock that protects all state modifications. Read operations such as instantiate and configuration exists acquire read locks, which permit concurrent access. Write operations such as register, unregister, and set configuration acquire exclusive write locks. Lock acquisition follows a consistent ordering to prevent deadlock. The maximum lock hold time for any single operation is bounded by the complexity of the operation. Error handling follows a standard pattern throughout the registry. All methods return an error code of type filter registry error. Codes include filter success, filter not found, filter already registered, filter invalid name, and filter internal error. The registry maintains an error state variable that stores the most recent error code. The getLastError method retrieves this value and clears it for the next operation. The registry maintains internal statistics that track the number of registered filters, the total number of instantiations performed, and cumulative lock contention metrics. These statistics are updated automatically and are read only from the external interface. The getStatistics method returns a snapshot of current values. Statistics are useful for performance analysis and debugging but do not affect filter behavior. Memory management for the registry is handled through a custom allocator that can be configured at initialization time. The registry does not perform any dynamic allocation during instantiation. All allocations occur during registration and configuration operations. Memory is reclaimed when filters are unregistered. The allocator interface is pluggable, allowing integration with application-level memory management systems. Configuration persistence allows the registry to save and load state from stable storage. The persist method serializes the current registry state including all registered filters and configuration parameters to a binary format. The load method reconstructs the registry state from a persisted file. Both operations are atomic with respect to external observers and do not require stopping active filter instances. The binary format for persistence uses a simple header-based structure. The header contains version information and metadata about the number of registered entries. Each entry includes the filter identifier, the length of associated configuration data, and the configuration bytes themselves. No checksums or error correction codes are employed. Format violations during load operations result in an error code. The registry supports hot reloading of filter definitions through the reload configuration method, which rereads persisted configuration without requiring application restart. Hot reloading does not affect instances that were already instantiated before the reload operation. New instantiations will use the reloaded configuration. The method is safe to call while other threads are accessing the registry. Query operations are provided to inspect configuration parameters for a given filter. The getParameter method accepts a filter identifier and a parameter name, returning the associated value or a null pointer if the parameter does not exist. The getAllParameters method returns all key-value pairs for a filter as a read-only structure. Parameters can be modified only through the setConfiguration method. Lifecycle hooks are supported through optional callback functions that are invoked during registration and unregistration. The registration hook callback is invoked immediately after a filter is registered. The unregistration hook callback is invoked immediately before a filter is unregistered. Hooks are not invoked during instantiation or configuration modification. Hooks run under the write lock and must complete quickly. The registry is initialized through the initialize method, which accepts optional parameters for allocator selection, lock type, and default configuration file path. After initialization, the registry is ready for registration operations. The shutdown method cleanly terminates the registry, unregistering all filters and releasing all allocated memory. Shutdown does not affect active filter instances. The caller is responsible for managing instance lifecycle.